Our speaker tonight is Professor Tony Prave from the School of Earth and Environmental Sciences, University of St Andrews. He is this year's recipient of the Clough Medal by the Edinburgh Geological Society, which is that society's premier award, presented to a geologist whose original work has materially increased the knowledge of the geology of Scotland and/or the north of England. For any geologist working in Scotland or the north of England who has significantly advanced the knowledge of any aspect of geology. Tony's academic qualifications were gained in the United States, which will probably work out from his accent when he does get around to speaking, from the Indiana University of Pennsylvania and latterly from Pennsylvania State University. From speaking to him tonight, I think he came over to St Andrews in the mid-90s, 1996 was mentioned, and I'm assuming he's been here ever since.
I'll switch into my St Andrews accent for the crowd.
Okay.
So
that may be too posh for us, I'm afraid. He's a member of a number of professional bodies and societies, European Union of Geoscientists, Geosciences, American Geophysical Union, Geological Society of America, the Geological Society of London, International Association of Sedimentologists, the Royal Society of Edinburgh, the Society of Economic Paleontologists and Mineralogists. I can't see anything about being a member of the Glasgow Geological Society, but we'll maybe work on that one with him. His research utilises field-based observations and isotope geochemistry to create, test, and constrain ideas about the processes that shape the Earth's surface environments. His interests are keenest on those pivotal times of geological history during which wholesale Earth system change occurred. He is a lead author on the Dalradian chapter of the new 5th edition of the Geology of Scotland book, which is scheduled for publication next summer, I believe.
Yes.
The aims here are to assess the most enduring theme about the Dalradian sedimentation, i.e. its origin in rift basins, and offer a revised geological evolutionary story. So that's enough of me, and let's go over to the main event. So it's over to you, Tony, and thank you very much for tonight.
Well, thank you for spending an evening with me, well, 45 or 50 minutes. Those were a lot of words. Basically, I like the stories that rocks contain. So I'm going to tell you a story about what some of the rocks contain and the rocks here in our homeland. And just to preface that before I do begin, I use the term Neoproterozoic for a time slice. If we look at the 4.5 billion years of Earth history, there are two time periods that stand out as being very, very profound in seeing entire wholesale change of the way our planet operated. One was what I think you've all probably have heard about, was when free oxygen became available in Earth's atmosphere and upper oceans, this great oxidation event around 2.5 billion years ago. The other one is this particular time slice. This is between 1,000 million and 600, 500 million or so years ago. And this is when animals evolved and what are arguably the most severe climatic episodes that ever influenced our planet. And so when I moved here 27, almost 28 years ago, it was like coming to a bit of Mecca, because the entire bit of the northern half of this country has rocks that record this particular time slice, which has been my interest for my professional career. So next slide, please. And as was already mentioned, just a little bit of self-promotion here in the sense of the Bible that we have all used for the last 20 years, and certainly when I came here, is the one that you see on your left, the Geology of Scotland, 2002. And the stories, the rock stories that we tell one another, that we've told students, largely are underpinned by the chapters that sit in that particular book. A new one is coming out, 5th edition, as you say, coming soon. It was supposed to be this year, but various issues have arisen, and it should be out next year. And if you go to the next slide, please, as was already mentioned, oh, sorry, I'm already one ahead of myself, so I'm trying to finish off early. If we went to that book, this particular time slice that we talk about, there were really 3 major take-home messages that we teach students, or we used to teach students, about the Dalradian supergroup of rocks And that is that these rocks that sit north of us were formed in rift basins, that the most iconic unit within this succession of rocks, the Port Askaig-Tillite, and you probably already have heard talks about the Port Askaig, this unit that represents one of these ancient climatic episodes, very severe glaciation, sometimes called snowball Earths, was 600 million years old, and that the start of Dalradian sedimentation was less than 750 million years. Now, I want to address those three issues because, as you'll see, this is more than just us talking about rocks in our homeland. The interest is in how we can tie the information that are contained within the rocks of Scotland to what we think we understand and know from those rocks of the same age worldwide. Next slide, please. And this is the Dalradian, right? It's sandwiched between the Highland Boundary Fault just to the north of us here and the Great Glen Fault. And I have two key messages I want to try and get across. The first is to address this issue of the birth of the Dalradian. Was it in rift basins, or can we think of a different mechanism for the initiation of sedimentation of this group of rocks? The second is to take the information that has been obtained since 2002 and put this into a context that we're going to see, next slide please, that there it is, comes out in a month or so with a cast of characters, not just me, because there have been a number of us that have been working on these rocks for the last 2 or 3 decades. And these are the ones that have contributed to the chapter that, yes, I'm a lead author on, but we've all contributed equally on this. And I'm doing that because I'm going to distribute blame everywhere if, this goes south. Okay, next slide, please. All right, when I arrived here, there was one statement that said everything about the Highlands, and it was this one. Jack Soper, Ian DL, a number of the great and good of those years said the secret of the Highlands is if it's Proterozoic, it's extensional. That was the long and the short of it, because everything since then was compressional, the caledonides, all the rest. The reason that this statement was made, next please, was that no matter where you went, when you looked at the supracrustal rocks, that is the sedimentary or metasedimentary packages that sit on all these beautiful granites and basement rocks that make up Scotland, every single one of those, starting with the oldest sedimentary rock unit in Britain, and as a matter of fact, one of the oldest non-metamorphosed sedimentary rock units anywhere in Europe, the Store Group, and as we come clockwise, looking at this array of cross sections, every single succession was formed in a rift basin. And not only were they formed in rift basins, you can see from those cross sections, every single rift basin looked about the same. Now, when I first saw this, the thing that struck me was that, next slide, please, is that represents 600 million years of nothing but rifting. Now, I just ask you to think yourself, if we think of the modern world, I'm talking Cambrian and onwards since I worked in the pre-Cambrian, you can't point to any place on Earth that has experienced one type of tectonism for 600 million years. Matter of fact, you can't point to any place on Earth that's really experienced it for 100 million years. Tectonics evolves. You go from rifts to passive margins, collisional basins, etc. Okay? So this really struck me as a bit odd. And basically, to cut to the chase, what has been recognized, next slide please, is that when you read the next edition of the Geology of Scotland, many of those rocks that we initially thought were formed in rift basins are now being recognized as having an origin other than that, and these are foreland basins resulting from collisional orogenesis. Those are not the topic that we're going to be focused on today. I want to talk about the evidence that we have for the Dalradian. Is there evidence for rifting and extensional tectonism in the Dalradian? And can that then be linked to what we understand for the North Atlantic region as a whole, and then put that into a context of what we understand for the Earth system as a whole during this particular time slice? So next slide, please. And yes, you know, all of you, if you are geologists, and if you did get your degrees in Scotland, you certainly would have seen a lot of evidence for rifting in these rocks for what we could label very simply the upper Dalradian. I'll stop here for a minute. The one thing I do not want to do is to get involved with a lot of stratigraphic nomenclature. I'm uncertain when I look at the faces here how much of these stratigraphic names you recognize. You know, they often make your eyeballs roll over in the back of your head. You know, when I was taught stratigraphy, you had to memorize all that kind of stuff. So I'm going to avoid that and just keep simple kinds of descriptions, upper Dalradian, lower Dalradian. We'll talk about certain groups of rocks, as I have here in terms of these cross sections, the Southern Highland group and the Argyll group. These are the upper two units of the Dalradian. But I don't want to digress into a lot of other stratigraphic terminology unless you all tell me you would like that, okay? And please, at any point, don't be polite and stop me if I'm saying something that you didn't quite understand, or I'm speaking too quickly, or my accent doesn't grind on your ears properly. So if we go back then to what I'm talking about, yes, you know, these cross-sectional views of these rocks in the Argyll and Southern Highland group, yeah, there is a lot of evidence for extensional tectonism. Next slide, please. All right, yeah. This university has given us the one and only single depositional age for this pile of rock that is many kilometers thick, that extends over several hundred kilometers. One depositional age, and that's Tim Dempster's age, is 601 million years up near the top of the Dalradian. I'll come back to that towards the end of the talk, okay? Next slide, please. There's our evidence, right? You can go anywhere in the world of any age rocks, and when you see these types of lithological characteristics, you begin to think, yes, you're looking at active tectonics. Top slide on the left is the Scarba conglomerate, named for the island. It's sitting offshore to the west here, just north of Jura. And there you can see a rock hammer for scale on this large boulder. This is an intraclastic or an intraformational breccia that's self-cannibalizing itself along these extensional or normal faults. The Barravulan boulder bed is one of these volcanic mass flow deposits. And on the right, probably the most uncontroversial bit of any evidence for extensional tectonism, pillow basalts. These are the Tavelic pillow lavas. And that age that Tim Dempster got was, if my memory's right, just 100 or 200 meters above these pillow basalts. So yes, there's extensional tectonism. We're extending and fracturing continental crust, tapping the mantle to get these types of volcanics, and in the process of doing that, generating these types of coarse clastic rocks that are infilling then these extensional basins. Next slide, please. But the question that I asked was, many of us asked, just not me, is, well, what is the evidence in the lower part of this suite of rocks, the lower part of the Dalradian, particularly in this Grampian and Appin group, okay? And I've highlighted here right at the base, this is the only other solid age constraint that we have to constrain the timing of deposition of these rocks. This is an age of 840 million years that is obtained on a suite of rocks that sit beneath the Dalradian, and they have been metamorphosed and migmatized. And the Dalradian does not contain that metamorphism or migmatization, so the Dalradian must be younger than that metamorphic event of 840. So that's it, two ages, 601 million up at the top, 840 million at the bottom. Now, you could argue a bit that there's this age or that age, or we correlate this rock with that rock, but that involves assumptions. These are the two solid ones that we have. Next slide, please. So this is the take-home message then. If we just stand back and look at what we've been told in 2002, the Bible of the Geology of Scotland, and previous to that these rocks have three key features. The extension that's occurring is in continental crust, not oceanic crust. That the basins, and there's the scale bar that is sitting on these cross-sectional views. I've just cut and pasted these from the 2002 edition. The basins are a few tens of kilometers in size, okay? And as you can see in these cross-sections, the basins are mostly half-grobens, okay? So every one of those cross-sections that I showed you, whether you go from the oldest sedimentary rocks right up through to these younger ones, are giving you that kind of cross-sectional view with those criteria. Now that's very good, because for me, coming from across the pond, where I have spent 40 years of my working career is, next slide please, in what is probably the most extended bit of continental crust on Earth, the Basin and Range Province. And the beauty is it is giving us geometries of basins that are exactly what are inferred for the Dalradian. This is an image of the western half or western third of southwestern third of the United States. Los Angeles there in the bottom corner, Las Vegas over the Denver. You can see the plate boundary of the San Andreas and this Jurassic arc of the Sierra Nevada. And sandwiched between the arc and the plate boundary in the unextended part of North America, next slide please, is the Basin and Range Province. And we're going to go to one place in particular that I've been very fortunate enough to work in, and that's Death Valley, which I've highlighted there. And next slide, please. Just to give you a sense of scale, there's Scotland, all right? And as I said, those basins that we have here, where we can go and walk around and look and not make assumptions about what we think might be the type of tectonics that's operating, we can see this in real life, you know, right there we can go. Next slide, please. And this is what one of these basins look like. That is Death Valley itself. You're looking more or less east-southeast. Badwater, it's 90 meters below sea level. This is the lowest point in the northern hemisphere. Next slide, please. And what you see are essentially the ranges that are bounding those basins. The rising footwall of the Death Valley Fault Zone. This is the Black Mountains. Dante's View is the top of the arrow, and that relief is 1.6 kilometers, a mile. What I'm standing on is this rotated, tilted fault block of the footwall. And I like this particular picture because I started cutting my teeth doing geology on that light-colored band of rock that you see there. That was my master's degree. It's one of these classic Cambrian quartz arenites, like the arable sandstone here in the north of Scotland. Next slide, please. It's going to be a bird's eye view now of what I've just showed you. Top left corner is where that photograph was taken, Algarberry Point. You're looking east-southeast. You can see Badwater and Dante's View highlighted. And the point that I want to make is this, is that in extended continental crust, one of the fingerprints that we want to look for is the nature of the infill of those basins. Yes, the structure is interesting, the faults are interesting, the basement rocks are interesting, but what tells us what type of tectonic setting we're in when we go back into the rock record looking at supracrustal rocks, that is sedimentary rocks, is the stratigraphic architecture and the sedimentary facies that infill those basins. And in this case, here is the scale of the basin that we saw in those cross-sectional views for the Grampian and Appin group, you know, a couple of tens of kilometers, and that when you look at the sediment infill, the key characteristic is the source areas are local. They're being fed from the rising footwall or the subsiding hanging wall. The multiple sediment influx centers, if you want to do sedimentary paleocurrent data analysis, this is the kind of characteristics you see. And you have different types of inflows into these basins. All right, next slide, please. And the infill of those basins can be quite dramatic. On the top left is Telescope Peak. This is the highest peak of the Panamint Range. It's the greatest relief that you have in North America. Ben Nevis, I put where Ben Nevis, the top of Ben Nevis would be. So that alluvial fan would bury Ben Nevis. If you go into the guts of that fan, what you see is in the bottom left. And what I've circled is my old field vehicle that I used to drive around, and that's an old CJ5 Willys Jeep. It's basically a leftover from World War II US Army vehicles. And you can see the type of characteristics of the rocks themselves. And what I want you to impress upon you is the slide on the right, is that these range blocks that you see, those mountains that are there, they are successively buried and onlapped by their own detritus. Okay? So this is the image that we need to have in our heads when we go back through time to look at what people are inferring are continental rift basins being infilled by sediment being derived from those bounding basin blocks. Next slide, please. Now, I'm basically a stratigrapher, and I don't mean stratigrapher in terms of paleontology. I mean a stratigrapher in terms of looking at layered rocks, sedimentary rocks. And what I want to highlight is that one of the single most characteristic features of sedimentary infill into rift basins is what I've labeled as abrupt lateral and vertical facies changes. And I'm going to take you on a picture tour, stop 1, 2, and 3, to show you what those characteristics are like in what is an exhumed extensional rift basin. This is the late Miocene China Ranch Basin. Okay, next slide, please. And there you are. You literally walk along that transect going from these very coarse, what are called fanglomeratic rocks, into these coarse and finer braided fluvial systems, and then into these very fine-grained basinal, center parts of these basinal infills. In this case, these are marls and mudstones, and this happens to be lacustrine, okay? But that's the typical characteristic. Next slide, please. And if we put the lateral vertical, because we know that, Volter's law tells us that those environments that existed laterally through time are stacked vertically. What we have, next slide, is this very systematic change fairly quickly over a few tens of meters, going from what would be a dominant environmental setting, like this lacustrine suite of mudstones, up into what is this interbedded mixed suite of facies, these mixed lacustrine braided fluvial. In a vertical sense, you have that change, but it also happens laterally. And what I've tried to highlight in red is where, if you were to go look at those rocks, you would see the braided fluvial systems, and these are interfingering with the more mud and marlstone rich lacustrine systems. And so this interfingering laterally, this interfingering vertically on tens to hundreds of meters scale. Okay, next slide, please. So, 4 things: local provenance, classed or angular, poorly sorted, abrupt lateral and vertical facies changes. This isn't nuclear physics, right? These are the types of things that we teach undergraduates to make the basic observations. So we have this as part of our toolkit in our back pocket when we go look at a sedimentary succession somewhere else in the world. And that's the kind of tick box exercise we want to have and do. Next slide, please. And the thing I want to highlight is some of you might be saying, yes, but often the Dalradian is subaqueous or submarine. Well, it doesn't matter. The facies characteristics are the same. And here's just a cutaway view of the Bray Basin in the North Sea, okay? It's the same type of thing that happens in a submarine setting as it does in a subaerial setting. All right. Next slide, please. Okay, now, enough of the sort of sedimentology lecture, and now to the rocks that you've come here to think about. This is the image that had transformed the thinking of the initiation of Dalradian sedimentation. This is the Grampian group basins. This is up near Inverness and Aviemore. This was work done principally by the BGS and their colleagues in the late 1800s, late 1980s and 1990s. And the hallmark or exemplar suite of basins and bounding ranges are there in what is known as the Coryeric and Strathtumwell Basin, separated by what you can see as the Glenbanker High. And this is the cross-section that Glover generated, showing his structural interpretation of those rocks that you have exposed there in this northeastern part of the Grampian Highlands. And this is the thing that I want to stress, is that the structural geology is beautiful that's been done. But quite often, and I'm saying this with structural geologists as colleagues, the structural geologists are interested in the cracks and fractures in the rocks. They're not necessarily interested in the rocks. And for me, it's just the opposite. I'm interested in the rocks. And for me, the cracks and fractures screw up the story, right? So this is the interpretation, fair enough, based on the structural geology. Now the thing is we want to go see what the sedimentary rocks look like that infill those basins. So can I have the next slide, please? All right. And I'm doing this because I took you to Death Valley, not because I wanted to show off that I was there for my master's degree, because it fits almost magically the Glenbanker High, Coryeric Basin, Strathtumwell Basin. Okay, next slide, please. So, this is like beating a dead horse. Local provenance, class or angular, poor sorting, abrupt lateral and vertical facies changes. That is what characterizes these rocks that are infilling basins in extended continental crust. Next slide, please. What do the rocks look like? Again, I don't want to bore you with formation or group names, but when you go there, and this might be hard to see at the bottom because of the lichen, but you can see these very rounded cobbles, lots of them. And they're separated from one another in this sandy matrix, but they're very well rounded. You look up at the top, it's a bit of a finer grained deposit, but again, it's relatively poorly sorted. But when you look at the clasts, most of those clasts are relatively round. They're not angular, okay? Even these finer grained clasts are relatively rounded. And these are our caustic sandstones and conglomerates. Next slide, please. The interesting aspect is, though, is that when you actually look at where they're being sourced, they're not being sourced anywhere near from the so-called basement bounding blocks of the Badenoch Group Glenbanker High. This is the age of the ridges that are separating the basins. This is where the material should be being fed into the basin. This is a detrital zircon age spectra. It's relative frequency on the y-axis, age on the x-axis. This is work that has been done by colleagues 20, 15, 10 years ago. And you can see from the age spectra that the detrital zircons that are part of the detritus, these are caustic sandstones and conglomerates are being derived, are based on these authors' interpretation coming from the closest rocks that match those ages is the Rins complex on your homeland of Isla, right? Okay, so not local. Next slide, please. More so, and to me, the thing that was striking is that when you actually look at the rocks that infill the basins, they are boring as hell. They are these relatively fine-grained turbidites, sediment gravity flow deposits. Mostly monotonous, they're relatively thick, many kilometers, fine-grained turbidites everywhere. Okay? There's no vertical and lateral facies changes. All right? So if we go to the next slide, please, here's our tick box exercise. Right? We have first, yes, we can say, next slide, please, poor sorting. Yes, okay, but also no, right? It's not everywhere. But the other three key characteristics, they're not there, all right? So you have to ask the question, yes, the structural geology is giving us a sense of looking at these blocks of rocks that are separated by faults, but the sediments that are associated with those do not have any of the facies or lithological characteristics that define infill of rift basins in continental crust. So why was this idea of rift basins and why has it persisted? Next slide, please. Interestingly enough, it's not the physical characteristics of the rocks that people latched onto to say these rocks represent a rift basin. It's based on an interpretation that limestones, this little thin blue line that you see just to the left of the Glenbanker High, are onlapping those basement rocks, those 840 million-year-old migmatized metamorphosed rocks. Next slide, please. This is a bit of a blow-up of that region. So here in blue are these younger rocks, the Iapetus group limestones, that, as you can see, as you progress northeastward, are progressively looking or appearing to be stepping downward onto these 840 million-year-old migmatized rocks. So here is an onlap. That means this must have been a paleotopographic high in order for onlap to occur. Next slide, please. I want to point out, and I'll point this out again, is this fault zone. The first name is, for my tongue, probably an unpronounceable Gaelic name, so I'm just going to call it the ABIM fault. It's been recognized for quite some time. Next slide, please. What was done was those limestones were sampled. And the argument was advanced that the chemistry of them, and particularly the calcium, iron, magnesium oxide ratios, placed on log plots, were able to distinguish and differentiate limestones that belong to the Iapetus group from limestones that did not belong to the Iapetus group. And what I've highlighted and what I'm going to go through the next several slides is talking about these Kinloch-Logan limestones, and there I've highlighted in blue where they occur within this iron, calcium, magnesium oxide space of the Iapetus group. Next slide, please. Now, there we are back to our map, okay? Next. The star represents where those samples come from that have been used as the basis to say that this swath of blue limestones in this part of the Grampian group are Appin group limestones. Now, when I plotted this up, I found that very curious because as I highlight, there's the crucial area where the limestones are actually more or less in contact with the so-called basin high. They're not separated by this fairly major fault. So, next slide, please. That's where I went to sample. Okay. So now we're going to have two data sets to compare. Next slide, please. All right. This is a slightly larger view. This map at the top is tilted so that north is pointing up to the northeast. You can see the black square of Aviemore to give you at least a geographic positioning. I have highlighted what are these two key areas. This Kinloch-Login area, which is the samples that were used to infer the Appin group limestones, and then this Cool Farm area, which is where I sampled, which is where the limestones are sitting, inferred to be sitting on the basement rocks, okay? I want to also highlight then, next slide please, there's that position of the fault, the samples that are separated from the basement by that fault that were used to infer Appin group, whereas the samples that I took, there's no real major structural complication there. Next slide please. And I'm going to point out several other areas in which there are limestones or marbles known within the Grampian group that people have studied and looked at. And the critical thing, next slide please, is this, is that we have the Grampian group section, we have the Appin group section. Between these two locations these two units that I'm highlighting, the Kincraig limestones, the Kinloch-Login limestones, they're separated by get my tongue working. The stratigraphic interval that separates them is many thousands of meters. Everyone agrees that the Kincraig limestones are Grampian group, and the inference is that the Kinloch-Login limestones are Appin group. Okay, so we have two data sets. We have samples that are coming from the same locality that are inferred to be onlapping a basement high. Next slide, please. Now, bear with me. Only look at the top panel, panel A, all right? What I have highlighted in the squares, the red squares, are these two limestone units, Kincraig and Cool Farm. Color coding is red is Grampian group, blue is Appin group. Doesn't matter what the names are, but that's what you want to keep in your mind. The top panels of that upper panel are just various elemental ratios and ternary diagrams the people who look at carbonate rocks use to try and separate and differentiate and discriminate between different source areas where some of the detritus coming into the carbonates could be identified and fingered. The take-home lesson is simply this, and I've blotted out, I've tried to damp out some of the other data because I just want you to focus on Cool Farm and Kincraig, Grampian group, Appin group. For those discrimination data sets, there is none. Statistically, they're the same. There's no differentiation, no difference between them, and though using that suite of elemental ratios. You can look at the spider diagrams. There is this difference with Dulnane Bridge. Again, we're not going to worry about that. One sample is a bit odd for the Cool Farm data sets, but otherwise, again, pretty much indistinguishable from rare earth element data. So, those data aren't really going to be telling us much. And the key thing is that let's go to the data set that was used to infer this Appin group correlation, apples with apples, rather than apples and oranges, that is calcium, iron, magnesium oxides. There's the data for Cool Farm and Kincraig. Remember, these are supposed to be different stratigraphic units, Grampian group, Appin group, and you can see they plot in a bit of a cluster. There's no differentiation between the Kincraig and Cool Farm data sets. Kincraig is undeniably Grampian group. More so, if we come over and look at panel C, I've taken the data that was published on the Kinloch-Login data set and incorporated the sample that I got from Cool Farm with the Kincraig data, and again, plot together. Next slide, please. Now, there's another suite of geochemical data, isotope data, that people have been using for several decades now to identify and use as a correlation tool carbonate rock units. And this is their carbon isotope signature. All right. So we've done that. We've taken those rocks and we've looked at what their carbon oxygen isotopic values are. And again, what I'm highlighting here in the top diagram are the data. And let's not worry about some correlations in terms of cross plots of carbon oxygen and potentially resetting. The key take-home message is that the Kinloch-Login data and the Coulthard-Kincaid data, that is the Grampian group data versus the Appin group data, seem to be separate in oxygen-carbon space. All right. And if we add then Appin group data to this diagram here in B, what we see is that the Kinloch-Login data, which are inferred to be Appin group, are indeed plotting with Appin group, but the Coulthard data, which is supposed to be that Appin group equivalent onlapping the basement, are plotting with the Kincaid, that is the Grampian group data. Is that clear? Clear as mud. Okay. So I'm just going to launch into this. You don't have to take my word for it. You can go and read lots of papers on this. But what I did then was to take the data that we have in terms of the carbon isotopes and do what all carbon isotope stratigraphers do, plot that stratigraphically as best we can with the understanding of what the stratigraphy is in that region. Next slide, please, which is what I did. And what you see, next slide, is that if we accept that the Coulthard-Kincaid data are part of the Grampian group, and the other data that I didn't talk about fit on this particular stratigraphic diagram where the y-axis is stratigraphy, the x-axis is carbon-oxygen isotope values, it defines a fairly reasonable systematic trend. Okay? This doesn't prove anything, but it defines a sensible trend. So next slide, please. So what we can conclude from the geochemical data sets is independent from the facies and sedimentology is that iron, calcium, magnesium log ratios are really inconclusive. They're not going to differentiate between carbonates of the Grampian Appin group, and to be blunt, they're not going to do it for any carbonate rock. Next slide, please. What we can say is that the Coulthard-Kincaid data have four characteristics that they share. Each grouping has an internal carbon isotope compatibility. The carbon isotope values of those strata are different from the Appin group. That the rocks that are associated with those limestones are similar and compatible between the two locations. And absence of evidence is not evidence for absence, but one of the striking things about the Appin group everywhere in the Dalradian is that there's this trinity of sort of associations of carbonate, quartzite, and graphitic schist. And they're not present in that Coulthard or Kincaid data, or those areas. Next slide, please. So, if we then look, what I hope is objectively, at these data sets of these limestones, marbles, that the Coulthard, those ones that are sitting directly on the inferred basement high, they're not Appin group, they're Grampian group. And therefore, if we combine that with the sedimentology, that says that there none of, or very few of the indicators that are hallmark indicators of deposition in rift basins are present, the only conclusion I think we can come to is, next slide, please, is that they're not deposited in rift basins. Okay? There's no rift basins. Now, you know, it's one thing to say what something is not. It's far more insightful, profound, and interesting if we say what it is. Next slide, please. Okay. So let's step off of our island and look around us in terms of what is understood at present for the tectonic geodynamical setting within which these rocks, or the timing within which these rocks were being deposited. This is a cartoon of Laurentia, North America, and Baltica. And the interpretation of the tectonic metamorphic data sets that have been generated for the Baltica area and Laurentian area, is that Baltica underwent this clockwise rotation from around 1,000 million years ago to about 600 or 700 million years ago. And in so doing, it generated these two orogenic events. In the north, it's called the Rhinelandian. It was around 900 million years ago. And as it rotated and closed and intersected what has become Scotland, it was the Neudartian orogeny at around 800 million years ago. And these are not my reconstructions. These are other workers' reconstructions. What I have highlighted, though, is the inferred, guesstimated position of where they think the Dalradian basins, that is the part of Scotland sitting south of the Great Glen Fault, or southeast of the Great Glen Fault, might have been positioned relative to this tectonic dance that was going on between Baltica and Laurentia. Okay? It's collisional tectonics. Continent-continent collision. Next slide, please. Now, I am interested in what's happening on Earth's surface, not so much what's happening in the mantle or lower crust. But when we think of what's happening at Earth's surface, that is a consequence of these plate tectonic interactions being driven by the mantle, the response at the surface is to create a foreland basin. Okay? So on the left is just, the world's most famous modern foreland basin, the Siwalik Basin of the Himalaya. Now, what I was interested was when I made this slide on the right and was looking at the Himalayan, next slide please, is the Siwalik Basin, oddly enough, is about the same size of what we see with the Baltica-Laurentia interaction. So if we want to have an image in our head of the interaction of these two major plates, the Himalaya is probably not a bad example, okay? Now, importantly, to come back to talking about the rocks rather than big picture plate tectonics, next slide, please, is that the stratigraphic fingerprint or the stratigraphic architecture of a foreland basin is what's known as a Flysch to Molosse succession. These two words have sort of gone out of favor, but I did my geology back in the 70s and 80s, and they were used then. And basically, they just talk about the fill of a basin. The deeper marine deposits, Flysch, versus the shallow marine fluvial deposits, the Molosse, all right? And there I've highlighted the Flysch Molosse of the Himalayan basin. Next slide, please. And again, to put everything into a scalar perspective, there's Scotland to scale for that basin. Remember, the interpretation of the Grampian group is it's turbidites. Now, the Flysch is turbidites. So what we're looking at is a postage stamp of a postage stamp of a postage stamp of a part of a sedimentary basin. Next slide, please. And I just want to hammer home this point of Flysch-Molosse successions. We see this in every collisional basin of any age, anywhere. This is probably the most studied Flysch-Molosse basin, the Swiss-German one. This is at the hinterland of the Alps. Next slide, please. And again, for scale, there's Scotland. And here you can see through time this succession going from Flysch to Molosse, going from these deeper marine rocks, turbidite sediment gravity flows up into the shallower marine fluvial deposits. Next slide, please. And I'm going to, again, beat this like a dead horse. Cretaceous interior seaway, there's the scale on the left-hand side. This was the subduction of the Farallon plate beneath Laurentia through most of the Mesozoic, and Flysch-Molosse successions. And they can be hierarchically stacked, these depositional cycles. But overall, every single one of these is giving us this turbiditic type deposits into these shallow marine fluvial deposits. And again, next slide, to keep everything into a perspective, there's Scotland, okay, for this scale. And what I should say is this, on the right, these are thousands of meters, on the right, this is hundreds of meters thick because this is the deep basin. This is just a Wheeler diagram. This is time, not thickness. I should have said that the y-axis is age. And on the left, the thicknesses there would have been 3, 4, 5 kilometers. Next slide, please. And this is a cutaway view then of our cousins across the Atlantic, the Appalachian Basin. And again, the same type of characteristics. This was during the Alleghanian Appalachian, or for us, the Hercynian Variscan orogeny. Next slide, please. The same type of succession. Flysch to Molosse, and next slide, please, Scotland for scale, okay? So the stratigraphic architecture, as I've had on the strap line at the top of a foreland basin, is Flysch to Molosse. Next slide. You know, don't reinvent the wheel, but actually sometimes you do have to reinvent the wheel. And the wheel that I'm going to reinvent, next slide, is this. We're going to go right back to the original data set. These are the cutaway diagrams that were published in those works 30 years ago. And if we look at them now with the eyes of a sedimentologist and a stratigrapher, next slide, what you see are not rift basin fields, but flysch to morass. So each of the observational data sets that were generated 30, 40 years ago, there's nothing wrong with them. It's just now the interpretation that we can make based on what we think we see, or not what we think we see, what we see of the rocks, the characteristics of the rocks. Next slide, please. Okay, so now we come back to our story, okay? It's one thing for me to stand here, you know, an ex-colonialist come over here and say, here's how you should be interpreting these rocks. And the thing that you cannot do is trample on what have been decades of very careful mapping. And the mapping in these areas has been and is very, very careful. There are different interpretations of that mapping. The interpretations that have risen to the fore are ones within which they ignored work that was done by people like Piasecki and some of his students temporarily, where they said that many of the faults that we are looking at in this part of the world had an original reverse or thrust geometry. And this is a valid comment because when you go and look at the kinematic indicators associated with these structures, you can find indicators that give you top up to the north as well as top down to the south, or southeast, northwest, all right? So there is an array of indicators. It depends on which ones you choose to give you the interpretation that you'd like. If we now know that the Appen group rocks, the inferred Appen group rocks, that blue line that are sitting on the basement, are Grampian group, not Appen group. That is, they are older than the Appen group. Next slide, please. You can keep your eye on the blue. They are now Grampian group. And what Piasecki and his students said years ago about the Anneck-Berg Inverpatic Marquis fault belt was that it was originally a thrust. In a very simple sense, older over younger, okay? Next slide, please. There have been geophysical data that have gone across, and we all know what geophysics is like, all right? In terms of interpreting wiggles and squiggles beneath our feet. But the point I want to make is that it does not violate that cross-sectional view if we interpret that as a thrust fault. Next slide, please, because it's almost there in the diagram itself, okay? Okay, next slide. So the 3 take-home lessons to match the 3 take-home lessons from the 2002. Oh dear, okay, I'll hurry up. No, sorry, I'm talking too slow. I will try and finish in 5-10 minutes, okay? Is that there's no evidence for the existence of rift basins in the lower Dalradian. Yes, plenty of evidence in the upper. The structural template of the highlands, we need to be thinking about this, probably looking at original thrust or reverse faults. And a viable scenario then for the initiation of sedimentation, it was linked to this Neudartian orogenic event, a collisional event, not an extensional event. Next slide. Now, as that slide shows, this may sound like a lot of British, Scottish navel gazing, but next slide. What we now recognize is that each of the major supergroups, the supracrustal rocks, the sedimentary units of the highland, next slide, have an origin in collisional orogenesis. Next slide. Yeah, there we go, sorry, right? They are bracketed by these orogenic episodes, right? Now that becomes important because next slide, it goes far beyond worrying about what Scotland is doing because these data fit into an array of data that are giving us paleogeographic images of what the Earth looked like tectonically in the past, supercontinents. If you believe in those, if you like Rodinia. But for the kind of thing that I do, and most importantly, as far as I'm concerned, those data, next slide please, are what fundamentally underpin our ideas about how we interpret the most severe environmental biospheric changes in Earth history. That is this time period of snowball Earth, these glacial events. So this is not just navel gazing. These are data that feed into these models that then become data sets that are fed into creating these type of climate dynamic models. Next slide, please. So, and this I'll try and go through much faster. It's 4 or 5 slides. So I want to put this into Neoproterozoic Earth system evolution. We look at, next slide, please, Earth history in the Neoproterozoic using 2 sets of glasses. One's these carbon isotope excursions, which I've highlighted, and that graph on the top is time on the x-axis, carbon isotope values on the y-axis. And you can see over this 3.5 billion years, the Neoproterozoic represents one of these times of major fluctuations in the carbon isotopes. Superimposed within that, then, are these major climatic episodes of what are known as the 3 major glaciations of that time. And these are pretty large-scale global glaciations. And again, whether you believe snowball Earth or not, doesn't matter to me. We know that there are these 3 glaciations. Those are the timings for them, okay? The Gaskiers, Marinone, and Sturtian. Next slide, please. Okay. You know, nobody has to talk about the Port Askeg here in Scotland. This is, as it says up in the tin, it's the in-your-face glaciation. This is Tony Spencer on the left, the person who worked on those rocks and has done probably the most magnificent the most magnificent amount of work of any of these rocks anywhere in the world. Beautiful great breccia, these dimictites and tills. This is this dramatic bubble, as it's called. It's a glaciatectonite. It's a block of dolomite that is deformed under a flowing ice sheet. Next slide, please. And this is where I'm going to be a little self-indulgent, because if you look, in 1999, I'd published a paper more or less telling you what I'm telling you now about this 4 deep, the Sturtian glaciation that the Port Askeg is, and then another glaciation higher up in the stratigraphy of the Dalradian. Next slide, please. And this was the response that it got. Now, to me, that is poetry. And I'm very proud of that. That is the best rejection I think anybody could ever have. I used to have this on my door for 20 years. Then when we moved buildings, I lost it. Prave's attempt represents not just a disregard, an Olympian disregard, for the decades of scholarly research, which more or less tells you what they thought of my research, right? So next slide, please. So this was the process. Reject, go ahead. Reject, go ahead, go ahead, go ahead, go ahead, bang. And I have to say, I was talking earlier. Roger Anderton, the doyen of the Dalradian, reviewed the Geological Magazine paper after all these rejections, and he said, I think this should be published. And it went against most of his ideas. So this tells you the quality of the scientist he is. Okay, next slide, please. And we've come full circle, because now nobody questions this at all, right? Here is the work in part that David's part of in terms of the Port Askeg. There's no question now about it being Sturtian, right? 660 to 760. But the question is where are the other 2 glacials in the Dalradian? Next slide, please. All right. Okay. And I'm just going to show you some pictures quickly. Next slide. This is Namibia. This is not Scotland. And one of the aspects of the glacial Neoproterozoic cryogenian glacials is that they have what is called a cap carbonate, and that whole cliff that you see above what is marked glacial surface on the left is a carbonate rock that was deposited post-glaciation during this period of climatic amelioration when the world became very warm. On the right is the glacial dimictite, the melt-back ice-rafted debris, and then the cap carbonate. And this is what people have in their minds when they think about thinking of Neoproterozoic glaciations, that or the Port Askeg. Next slide, please. But that's only when you're sitting in nice shelf areas, shallow water. If you go into the guts of sedimentary basins, that is into the deeper basinal settings, the magnificent cliff of carbonate I showed you is reduced to what you see there sitting on the hammer on the left, or it's sillimanite facies on the right with the marker pen. These are the cap carbonates. How do we know? Next slide, please. Because sitting directly underneath them are drop stones. Okay. Scotland has exactly that. Next slide, please. This little squishy, what George Barrow mapped and called his little brown limestone through Perthshire. And locally, in places, that's what you see, drop stones underneath it. Next slide, please. The younger glacial we've known about for a long time. This is McDuff Boulder Bed. It's up on the north coast. And there's also down in the Kintyre Peninsula, the Loch Nakill Boulder Bed. These are drop stones. Size doesn't matter for drop stones. There's the big granite boulder on the left that everybody sees, but when you walk around that outcrop, you get beautiful little drop stones that are the size of, you know, a pence. Next slide, please. And associated with that, and I won't go into this, this is work that we've done. Yes, we have the carbon isotopes excursions. We have them from Ireland on the left. We have them on mainland Scotland on the right. We have them from Shetland, or sorry, mainland Scotland in the middle, Shetland on the right. Next slide, please. And we can now put the Dalradian into its proper place in Neoproterozoic Earth history. Next slide. We have a physical stratigraphy that's independent of any kind of chemistry. Next slide. We have the chemostratigraphy and isotope geochemistry that allows us to link the Dalradian to what we see in many places. Next slide, please. These are reproducible right across the Dalradian outcrop belt. Next slide, please. They're compatible with what we know from Neoproterozoic rocks worldwide. Next slide, please. And oddly enough, a very weird occurrence that this department, Tim Dempster, found, this ichhyite, which is a cold water polymorphic calcite. You have to have very cold waters for this to form it. It has been found at about the level of what is being inferred as the Marinoan glaciation. Next slide, please. And this is where I come back to those two ages I talked about. All this fits very nicely within the age constraints. Okay, and it gives us a tasteful amount of time for the Dalradian, 130, 100 million years for the upper and lower. Next slide, please. All right. So, next slide. No, the Port Askeg is not Sturtium. This comes from data that people generated a geochronological method known as Rhenium-osmium dating. We don't need to go into the details, but what was established about 10 years ago, 12 years ago now, was an age in the Bella Hoolish rocks, and you can see they sit below all these inferred glacials, and a number came out at about 660, meaning that everything above it must be younger. Next slide, please. Interestingly enough, those same authors, as they studied places worldwide, recognized, well, maybe there's a problem. And this is probably the nicest way of saying we think it's wrong. Additional tests and geochronological constraints are necessary to fully resolve the complexities of the Dalradian. Okay? So those same authors questioning our data. But a handful of months ago, and I have to bring this up because we have to address these things. Next slide. A paper was published by Moles and Selby in which the amphibolite facies Aberfeldy barite deposit, those dark pyrites, were dated using the Rhenium-osmium method. They're diagenetic. We can all see this. They're overgrowing the fabric. But they were interpreted as syn depositional. And there is a line of reasoning that they put forth to say these are syn depositional. And I struggle with this. I don't struggle because of the age. I'm not questioning the age. But when you look at this, if you gave this to a first-year student, you'd say these large pyrites are overgrown, and they're pretty ugly pyrites. It's not like they're nice pyrites, right? Next slide, please. And what, for the life of me, I can't understand, there's a ready-made explanation for these, because the Dempster age on the 601 ash beds is dating this volcanic episode that occurred everywhere across the highlands. So you have ready-made, reducing fluids coming through to give you these pyrites. So next slide. But no, everything I've just told you is wrong. Okay? As it says in the blue box at the top, the Port Askeg is Marinoan. The ages of the Rhenium-osmium are right. Everything else is incorrect. So what I'm going to do is present to all of you to make up your own mind. Next slide, please. We're going to do a tick box exercise. We have the Dalradian is per inferred global correlations. The Dalradian is per Moles and Selby. We have a reproducible framework of 3 glacials. Next slide. Yes and no. Stratigraphic framework, a cap carbonate. Yes and no. Strontium isotope trend. This is something that Ian Fairchild and them have done, and this is critical because strontium isotopes have been shown worldwide to follow a trend that is reproducible from craton to craton to craton. Yes and no. Next slide. Next slide. Next slide. Next slide. You make up your mind. Okay? All right, it's up to you. I know what way my mind's made up. And until we get a reliable uranium-lead zircon age, I will be very happy with that age as a great rhenium osmium age, and its dating diagenesis associated with the volcanism at 600 million years. Next slide, please. So we can conclude then, in my myopia and my prejudice, that the Grampian group can be placed in a Neoproterozoic history that recognizes climatic environmental changes and a tectonic history. Neodychian orogeny, a collisional flysch-molasse basin. Next slide, please. A post-orogenic marine successor overstep basin, which happens worldwide in every collisional basin in the world. This is the middle part of the Dalradian. And then finally, yes, we get to the breakup of the supercontinent Rodinia, rift basins, igneous activity, Southern Highland group, et cetera, and the opening of the Iapetus. A nice, neat, clean story, if it's right. Might not be. Next slide, please. So the secret of the highlands, if it's Proterozoic, it's extensional, I'd say, well, it's complicated. Okay. And so for me, coming here 27 years ago, wanting to think about Neoproterozoic Earth history, looking at the rocks that are iconic to this, I was taught these rocks sitting in America in the 1970s and 80s. Next slide. The lesson that I've learned is simply that. Keep calm and stay open-minded. Thank you, and I'm sorry it took so long.